السلام عليكم ورحمة الله وبركاته. يسعد صباحكم. اليوم رايحين نكمل إن شاء الله السلايدات. So stop last time in this slide. So this slide will talk about quasi-equilibrium process. Okay. So in the previous slide we saw the isothermal process, isobaric process, and isochoric process. Isothermal means temperature equal to constant value. Okay. And isobaric means pressure equal to constant value. Okay. So if we saw those statements in a problem, so we should take an action that maybe temperature constant, pressure constant. If it is isochoric, then volume is constant. Okay. So this is we talked last time. So let's continue with the quasi-equilibrium process. So what is the first indication we should consider when we read quasi-equilibrium process? During the quasi-static or quasi-equilibrium process, the system, this is the meaning, the system remains close to equilibrium state all the times. Okay, or sometimes we call it ideal. Okay, ideal process. So let us understand it more precisely. So let's see this example. Here we have piston and cylinder assembly. Okay, so here is the piston and that one is the cylinder. So this piston cylinder was here, state 1. Okay, and this is state 1 moves until it reaches this state 1, and this is the flow of the process until we reach state 2. So this is compression process. Okay, so this is pressure versus volume. So volume decrease, that means we have compression. Okay, now during traveling from state 1 to state 2, we call this line path line, okay, or a process path. Okay, at certain instant, this one for example here, before reaching state 2, okay, we measure the pressure and we find it equal to 20. This is 20 is the points at each point on the piston. Okay, so along the piston the pressure is the same. Okay, so let's go back to the sentence. The system remains close to equilibrium state at all times. So if the piston move a little bit up to here, so we expect that the pressure along the piston will be the same. For example, 40, because pressure increased while volume decreased. But when this process or condition happens when it is sufficiently slow process that allows system to adjust itself internally, so that properties in one part of the system, for example this part, okay, do not change any faster than those at the other parts. Other parts, it could be at the middle here, it could be far at the edge here, okay? So at all parts, at any instance, the property, for example, pressure is the same. Compression is very slow. This is very slow process, so the system will adjust itself, and thus equilibrium is attained. We can reach the equilibrium very easily with a slow process at any immediate or intermediate state. So this is starting state and this is ending state, and those states are called intermediate states. Okay, here it is, intermediate state. Therefore, the intermediate states can be determined and process path can be drawn easily. So the process line will be continuous line, as you can see. Okay, let me erase everything. So as you can see, we can easily draw the path line, which is in this case, continuous line. It is an idealized process. It is not a real process. It is an ideal process. So whenever we hear quasi-equilibrium, it means we have an ideal process. But many processes closely approximate it with negligible error. So even in actual, we can approximately approach this line. Okay, even if it is far. Let us see an example. So such process we call it non-quasi-equilibrium or actual process. Okay, for bad writing. Okay, so same example, but now we have an actual case. So here we have volume, here we have pressure. Okay, this is the piston cylinder assembly. Here is the state 1. Okay, and we take an intermediate state, this one for example. Here you can see that the parts are not the same along the piston. Okay, so if we wish to draw to put a point on BV diagram, so the points will be, here we have this yellow color means 20 Pascal, and here red color almost 90 at the middle. Okay, because the color is, it's not the same along this line. Okay, so actually our points along the piston ranging from 90 to 20. Okay, so we have point here, we have point there, we have point there, okay, etc. But it's ranging from 20 to 90. So if we go further down, if we decrease the volume, so we'll reach another point where pressure again ranged from certain values. Okay, like this. So we cannot say that we have continuous line. We'll take best fit line. Okay, and you can see here the continuous line converted to dashed line. Okay, so this is best fit or approximated to the ideal line. So compression process is fast. Here in the actual scenario, we have very fast process, and this fast process, and thus the equilibrium state cannot be attained. So we cannot reach to equilibrium state as we did earlier in the previous slide. Intermediate states, okay, and intermediate states cannot be determined. We have a scattered behavior. We have a range from 90 to 20. And the process path, as a result, the process path cannot be defined. We cannot find it exactly. We can approximate it, but we cannot find it exactly. Instead, what we'll do, what is the solution? We represent it as a dashed line, okay? So this is approximated line. Here we have dashed line. Okay. Forms of energy. Forms of energy that we'll tackle here in this part, we'll talk about, let's see first the general equation. So in the absence of magnetic, so we have forms of energy. It could be magnetic, electrical, surface tension. But in the absence of these four energies, okay, the total energy of a system consists of kinetic, potential, and internal energy, as expressed in this equation. So here is the total energy, capital E, uppercase, which is equal to internal energy. This is internal. Okay. Kinetic energy and potential energy. And notice that all of the letters are written in the uppercase, and their unit is joule. Okay. So whenever we write energy uppercase, could be E, total energy, it could be work, okay? It could be Q, heat, okay? It could be potential, it could be kinetic. So all of them, its unit is joule or kilojoule or megajoule, etc. Okay. Now, if we wish to write them in lowercase, such as here, lowercase e, lowercase u, here v squared over 2, g, z, okay? So the unit will be joule per kilogram. So for example, total energy equal to mass multiplied by energy. So the unit for this term is joule, and the unit for mass, as you know, kilogram, and the unit for lowercase energy as a result, it is mass or energy divided by mass, which is joule per kilogram. Okay. Now, if you wish to write kilojoule, so it depends on the question. It could be kilojoule, megajoule, or joule. Okay. So the transfer from this equation to this equation, we must first write it in mass basis. Mass multiplied by energy, mass multiplied by internal energy, mass multiplied by kinetic energy, and mass multiplied by G multiplied by Z. Now, temperature and zeroth law of thermodynamics. Zeroth law. Remember, we start with the laws of thermodynamics, and we said that we have zeroth, we have first law, second law, third law. Now, the zeroth law, take a look to this diagram here, or picture. So here we have body A, body B, body C. So the zeroth law says that if body A and B are in thermal equilibrium, and if B is in thermal equilibrium with C, so if B and C in thermal equilibrium and A and B in thermal equilibrium, that means as a result A and C also in thermal equilibrium. Okay, so the zeroth law of thermodynamics: if two bodies A, B, B, C are in thermal equilibrium with, this is the keyword, okay, with a third body, they are also in thermal equilibrium with each other. Okay, so the equality of temperature is the only requirement for thermal. Now, the temperature scale, sometimes we need to convert the temperature. So here is the most important conversion. So usually we deal with Celsius, okay, degree Celsius, but sometimes we need to convert to absolute temperature or Kelvin temperature. Okay, so if we wish to convert from Celsius to Kelvin, we must add 273.15. Okay, other conversion for British unit, so we'll not use it a lot here in this course. Okay, but here is the conversion. This is Rankine, okay, with Kelvin, and here Fahrenheit with the Celsius. So in thermodynamics, it's desired to have a temperature scale that is independent of the properties of any substance, as we mentioned earlier. Note, it makes no difference to use Kelvin or Celsius in formulas involving temperature difference. What does that mean? It means that if we have delta T in an equation, so there is no difference whether we use the temperature as Kelvin or we use temperature as Celsius, because at the end we'll get the difference between them. However, you should use absolute. Absolute means we should use Kelvin, absolute temperature, and formulas involving temperature only. So if we have equation with only symbol T, then we should stick with the Kelvin or absolute temperature. Like example, ideal gas law, which is say that VB equal M MR sorry MR T. Here we must use absolute temperature. And those are the most common quantity. For example, we will stick with the SI units, so mass, length, time, force, already known for you, okay, and you are familiar with those units. Now, British unit for mass unit, length, time, force, so those are the units. Now, let's see example. Of course, we still we are developing the principle here, but it's good to do some practice on the principle that we uh, explain it to you. Okay, a spherical balloon. This is the shape of the geometry, holding 16 kilogram. This is mass of air. This is the substance inside the balloon. Has a diameter. This balloon, its diameter is a 3 meter. For the air, determine the specific volume. Okay, n meter cube per kilogram. This is the unit. Specific volume, or specific volume in terms of meter cube per kilomole. Also determine the weight of the air in unit of Newton. Use the acceleration gravity of 9.8, and I will add here 1. Okay, let's see. Let's move to the solving board. Now the question is, we have a balloon. Okay, this balloon filled with air, and this balloon is a spherical shape. Now we need to find out, first of all, the specific volume, which is small v, in unit of meter cube per kilogram. And that means we need to find the volume of the air, or of the occupied air, divided by mass. Mass is directly given, but we need the volume. So this is a balloon with a diameter of 3 meter. Then V of the spherical shape is equal to 4 over 3 by r cube. So if this is radius, then if this is diameter, then 4 over 3 by multiplied by 3 over 2 to the power 3. Okay, so this is the volume. So if you calculate the volume, you will find out that this is 14.13 meter cube. This is volume. Now specific volume equal to volume divided by mass, and this is equal to 14.23 divided by mass of the air enclosed in this shape, which is 16 kilogram. So 14.13 divided by 16, this is equal to 0.883 meter cube per kilogram. Okay. Now, the other requirement of this part is to find specific volume in terms of meter cube per kilomole. So in order to convert this unit into meter cube per kilomole, we need to find out the molecular weight of the air. Now, if you move to the, if you go to the Moodle, you will find this folder, which is Engineering Thermodynamic Appendix, first 50 page. I need from you to print out the first 50 page. Now, since we have a distance learning and we learn on everything is soft copy, so stick with the PDF file without print it out. Okay, so if you go to this file and download it from Moodle, okay, you will find out that this is appendix of our book, and its name is Property Table and Charts in SI unit. So first 50 page in SI unit. Now, I need the property of air, so I will go to the first table, table A1, and I will look out for air. Here is the air. So the molar mass or molecular weight of air is 28.97 kilogram per kilomole. Okay. Now, if we go back to our solving board, we'll write out that this is this value 0.883 meter cube per kilogram multiplied by molecular weight, which is 28.97 kilogram per kilomole. And kilogram cancel out with kilogram, and we end up with 25.58 meter cube per kilomole. So this is part A. Now let's move to part B. We need the weight of the enclosed air. Weight equal to mass multiplied by gravitational acceleration, and this is equal to 16 multiplied by 981, and this is equal to 156.96 Newton. Okay, so this is the first problem. Let's see another problem. So here in this problem, we have a closed system, and I'm sure you are pretty know what is the meaning of a closed system. Closed system means there is no mass crossing the boundary. Only energy can cross the boundary. So we have a closed system consisting of 5 kilogram. This is mass of whom? Of a gas. So this is mass of a gas. This is the substance. Undergoes a process. So we have, whenever we heard process, that means we have initial state and final state. Okay. During which the relationship between pressure and specific volume is, and we have an equation for that curve. Okay. So in this question, it says that we have a relation between the pressure and specific volume. Between the pressure and specific volume, small v, and this relation, okay, is BV to the power 1.3 equal to constant. Okay, so this is the relation, and we can tell easily that this state starts with high pressure and this one ends with low pressure. Then we have expansion. Okay, so this is state 1, very high pressure, and V1 for sure. Oops. Okay, so we have V1 and we have V1. V1 1 bar and B2 0.25. So here is B2 and V2. So B2 is here 1 bar and here we have 0.25. Okay, and this relation is equal to BV to the power 1.3 equal constant value. So we need to find out the final volume. The final volume in this question he has about V2. And the unit is must be in meter cube. Okay, let's move to solving board. So here in solving board, I'll start with drawing the VV. So here is specific volume. This is the pressure. We start from 1 up to 2. State 1, and here we have state 2. So V1 is given 1 bar. V1 is given again, which is 0.2 meter cube per kilogram. V2 given to be 0.25 bar. Okay. Now we need to find out V2. Now the relation given in this, no, we need to find not V2, we need to find the volume, not the specific one. Now the relation given V1 to the power 1.3, so this power only for V, equal to V2 equal or raised to the power 1.3. Now V2 is the needed quantity, so V2 to the power 1.3 equal to V1 over V2 the power multiplied by V1 specific to the power 1.3. Okay, so this is equal. No need actually to convert the pressure from bar to Pascal because those units will cancel out. So B1 given to B1 divided by 0.25 multiplied by specific volume which is 0.2 to the power 1.3. On the other side we have B2 to the power 1.3. And this is equal V2 equal 0.493 to the power 1 over 1.3. Then V2 equal 0.58 meter cube per kilogram. But the question asks for the volume, not the specific volume. He needs the volume in meter cube. So V2 equal to mass multiplied by V2. Mass is known. Why it's known? Because we have a closed system. Closed system means it remains constant. So this mass valid for M1 and M2. Okay, so let me go back to the solving board. So this is 5 multiplied by 0.58 and the 2.9 meter cube. Notice that to check your value, your answer, okay, that V2 or V1 starting from or specific volume, let me say that, starting from 0.2 and end up with 0.58. Okay, so as we expect that the volume increase. So that's it for today for Sunday lecture. See you in Tuesday lecture. Bye bye.